today we're going to be talking about calculus, finally. So what we're going to be looking at first is we have the word gradient used in our textbook a lot. So gradient is another word for slope. It means slope of a linear function, which we should be good at that, right? We say slope is the m value, or it's the rise over run. Okay. We say it's the difference in y's minus the difference in x's. Anything like that. That's all slope of a linear function. So the whole purpose of calculus is to go ahead and find areas under curves. So we need to find slopes of curved functions. And that can get a little tricky. So the first thing I have for you guys is an investigation from the textbook. It says, consider the curve y equals x squared shown below. Give the range of x for which the gradient, so that's the slope, of the curve is negative. Find out when it's positive and find out when it's 0. All right. So basically we want to look at when is the function decreasing, when's it 0, and when's it increasing. That's what it means when we're talking about slope. Is you're basically looking at when is the function decreasing, when's it increasing, when's it 0. So go ahead and take a second and enter questions A and B for problem 1 here. Now, the next part says the tangent to a curve at a point is a straight line that just touches but does not cross the curve at that point. All right, so it is possible that it crosses the curve at another point, but not at the point of the tangent line. So what I'm going to ask you guys to do now is on your graphing calculator or on other software, plot the curve y equals x squared and draw the tangent at the point 1, 1 as shown below. So there is a way to draw tangent lines on your graphing calculator. I've attached a YouTube video on the Canvas page. That's the idea with these values. Okay. Excuse me. So does this fit your expression in part F? Let's say it does. Okay, we had slopes that were getting closer and closer to 2. And then finally it settles on 2 when we get right to it, when we square it. Okay. So a couple things here. It says the gradient of a tangent is the limit of a secant. So there's a lot of words there. Saying the slope of a tangent line is the limit of a secant line is basically what it's saying. A secant line is like a chord. It goes, except it goes through 2 points and it keeps going. A chord just goes from point to point. So that's the difference there. And we don't need to worry about that definition too much right now. The big things we want to look at is the average rate of change between 2 points is the same as the slope of the secant between the 2 points. So it's just basically saying that the average rate of change should be the same as the, oh shoot. Hope I don't lose you guys. We just had a power surge, so I'm making sure you're okay. Are we still here? We're still good? You guys still here?
Yeah.
Okay, perfect. Just making sure. I had a power surge, so I want to make sure. I saw the lights flicker. Okay. So anyway, what I was saying is whenever we have a curve, like let's just draw one here real quick. Something that looks nice and big like that. And let's say we want to find the average slope between these 2 points. If I do, hey, let's find the slope at this point, the slope at this point, the slope at this point, which means we're finding a ton of tangent lines, and the slope at all of them. The average is going to be the slope of this entire line. If we do the rise over run of the entire line. That's what this is saying here with the average rate of change here. Okay? That's the idea. Now, what the gradient function is called, the slope function, if we can find it, it's called a derivative. And that's the first thing we're going to learn in calculus here. Now, one thing your book doesn't do, it doesn't show us the old school method of calculating a derivative by hand, which is a good thing. If I were teaching this class this is my first time teaching the class, so first time teaching this lesson for you guys, I probably would show you that old school method, but I think that's also really hard to do with this online teaching. So we're going to skip the old school method of how to calculate these by hand, which could be a little confusing because that's a good conceptual thing. But I will show you how to find derivatives of functions. So the derivative is going to be denoted by f prime of x. So it looks like f of x, except it's got a little tick mark on it. F prime of x is going to be a derivative. Okay, an alternative way you could see the derivative written is called dy dx. Okay. Dy dx is another way to write the derivative as well. Either one is perfectly fine. I think sometimes one is used over the other, but it just means the derivative of y with respect to the derivative of x. And then it also says you could do ds over dt, which is like speed and time, dv over dt is volume and temperature, or volume and time. You know, there's a lot of different things we could do derivatives with. All right, so we're only going to do one example today, but it's going to be 6 problems of it. It says find the derivatives of each of the following functions, and then find the gradient of the tangent line at the point where x equals 2. So the derivatives of the following functions, the way we find a derivative, we could do what we did in the investigation, which is where you find the slope several times over again. That's kind of a long way to do it. What really happens with a derivative, like we had the first function was y equals x squared. The shortcut way, which was really annoying because I remember when I was in calculus in high school, we did we had to do it all by hand, and we spent like 2 weeks doing it, and then after 2 weeks they teach you the shortcut way where they're like, hey, whatever the exponent is, you're going to take that and you're going to drop it out front, and then the new exponent is 1 degree less than the old exponent. So you drop it out front and multiply it by everything, and the new exponent is 1 degree less. So now let's look at it on a different problem here. The exponent in this problem is 4. This is 3x to the 4th. So what we're going to do is we're going to say 3 times 4x to the 3rd. We drop this down 1 degree, and we drop the 4 out in front, and we're multiplying it by everything. So 3 times 4 is, or we'll call this y prime, by the way. So 3 times 4 is 12, so this is 12x to the 3rd. That's the derivative of 3x to the 4th. So that's what a derivative is. So these first few problems aren't too bad, but they get a little trickier. We'll go into a little more in depth on derivatives. But that's the idea. Let's take a look at another one. Problem 2 here. Derivative. Hey, that's a 3rd power. So what I'm going to do is I'm going to say y prime equals 5 times 3 x squared. Drop the power of the function by 1. And you're probably asking, why do we do that? And the short answer is I didn't show you the longhand method how to do it, so it probably won't make any sense to you at all. But for some reason your book doesn't show the longhand method either, which I thought was really weird, because I'd have to go do some serious research to remember how to do it myself. But that's how we find derivatives. We're writing an equation that's going to help us calculate the the tangent lines, the slope of the curves, basically. All right. Now, problem 3, this is where it gets a little bit trickier. we treat each plus sign independent, each symbol plus and minus independent of each other. So we're going to take the derivative of each individual part. So hopefully it's not too bad for us. So let's do this in red. We deal with the first part, 2x to the third, 2 times 3x squared. And then we put a plus sign in. And then we're going to deal with the second part. So what happens is this is 3x to the first power. So this is going to be 3 times 1 x to the 0 power. Okay. And then minus 5, but guess what? There was next to the 0 power next to the 5, so that one actually just goes away. We lose the 5 completely. So what happens in this problem, y prime equals 2 times 3 is 6x squared plus 3. And that's x to the 0 power, so it's just 6x squared plus 3. It becomes 1 power lower than it was, and then we lose the negative 5 to the ether. It's gone. Gone forever. All right. But that's what problem 3 should look like. Okay.
Do you lose the negative 5 because like you can't have more than one x to the 0 or anything to the 0? Is that why? Or is it just like...
No, that's exactly right. Yeah. So whenever you have a constant term, there's no x to take the derivative of. So it's x to, it's what's happening is, I guess the best way to describe it is it would be x, it'd be, here, let's do this. Oops. So here's the best way to describe it. What happens is x moves into a negative direction. Remember how in the beginning of the day, I said, hey, we want to rewrite x as negative exponents? Because what happens is this becomes 5 times 0 times x to the negative first power. So what happens is I get 0 times x to the negative first power. 0 times anything is just 0. So that goes away. So that's why there's no 0 there. Does that make a little more sense?
Yeah, thank you.
Okay, good. Yeah, so that's...
I didn't understand that.
What'd you say?
I think I'm just going to pretend I understood that.
Okay. So, yeah, whatever happens, every time we're taking the degree, we're taking one number away from the degree of the polynomial. And in this case, because 0 times anything is 0, so it all goes away. That's what happens in this case. But that means the good news is we don't have to deal with fractions then. Let's take a look at problem 4. Y prime x squared, that's a 2x. We break it down by parts, remember? And then we have 2x plus 1. That's going to be at plus 2. And then plus 0. So it's really just 2x plus 2. That's our derivative for this one. Again, this drops to 2x to the first power. This becomes 2 times 1 times x to the 0 power. And this becomes... Oh, let's do this a little better. I'll show you the full handwritten version again, just to make it a little easier for us. So when we get good at it, we don't need to write all of this out, but it's going to be 2x to the first power plus 2 times 1 x to the 0 power plus 1 times 0 times x to the negative first power. And then y prime becomes 2x plus 2 when it's all simplified. We have x to the 0 power is just a 1. 0 times anything is just a 0. So that's how that one simplifies up for us. Okay. That's how we do derivatives. And like I said, when I was in high school, I sucked at calculus. I was not good at this. I took it my senior year of high school. Except our whole school year was spent on calculus. We're only going to spend calculus for the last month of this class. All right. Let's go ahead and take a look at problem 5 here. The first thing I want to do is I want to rewrite it. going to rewrite 2 over x as 2x to the negative first power. And it does say x cannot equal 0, and that's a good rule of thumb because we don't want a 0 in the denominator. That makes an undefined function. So now, what happens in this one, I'm going to say 2 times negative 1, x to the negative 2 power.
Wait, so how did you get the, because I understand that the x to the negative 1, that puts it up on the top.
Yes.
Why did you multiply it by 2? Because that's not the exponent.
Oh, no. It was multiplied by 2 because it was 2 over x. So what happens when you're doing 2 divided by x, you can rewrite it as 2 times x to the negative first power. Okay, so great question there. That's where the 2 comes from. The 2 was always there. It was just always in the numerator of the problem. Okay. Now what happens when I'm taking the derivative? Notice the derivative, I did the y prime here. I'll do that in green. Y prime. And then I did negative 1, and then I changed that to a negative 2 there. 1 degree less. And then the second part, x to the first power, is just going to be 1 times x to the 0 power. So y prime equals negative 2, x to the negative 2 power.
Where did the negative
Plus
2x?
Where'd the negative what? The x to the negative 2 power come from?
Yeah.
Excuse me. So what happens is every time we take a derivative, the exponent decreases by 1. So on like this first problem, the exponent was 4, it became a 3. The exponent was 3, it became a 2. The exponent was 3, it became a 2. The exponent was 2, it became a 1. Now this time the exponent was negative 1, so it became a negative 2 because that's decreasing by 1. That's where the negative 2 came from. I know, this is really weird. This is our first ever time seeing these derivatives. And I'm just throwing you guys straight into the deep end here. So that's what's happening with this particular problem. That's how we find a general derivative. And then last problem, problem number 6 here, y equals 3 over x squared. We're going to write that as y equals 3 times x to the negative 2 power. And then what happens is we say 3 times negative 2 x to the negative 3 power. We drop that degree of that polynomial by 1. And 3 times negative 2 is negative 6. Negative 6x to the negative third. Okay. That's how we deal with exponents in these particular problems. Okay. So now that's the first thing it asks us to do. Second thing it asks us to do is now go ahead and find the gradient of the tangent at the point where x equals 2. So basically it's saying find the slope, okay, of the tangent line.
Oh man, I thought that was the end.
No, unfortunately it's not. Find the slope when x equals 2. So basically it means we're going to plug in 2 to all of these problems. So 12 times 2 to the third. That's 12 times 8. 96. That's the slope. So the slope is 96 for the first problem. At that point. Second problem, 15 times 2 squared. Just plug in 2 for all of them. So what I want you guys to do is go ahead and plug in 2 for each of these other 5 problems and see if you can identify what the slope is going to be for each one. Okay, when we plug in 2 for them. Okay. So for our slopes of each of these points, I ended up with 96, 60, 27, 6, 1/2, negative 3/4. Hopefully that part wasn't too tough for you. It's just more trying to figure out what the problem's asking, I'd say. It was probably the hardest part. That's why I wanted to go through it with you guys. But that's really what's going on with these particular problems. Now, for parts, it says for parts 3 and 5. So basically problems 3 and 5, I want you to sketch the function and its derivative on the same axes and say whether the function is increasing or decreasing at the point where x equals 2. And the biggest hint I can give you is when it's increasing or decreasing at that value, we can just look at the slope, right? What happens if it's increasing? Is the slope going to be positive or negative when it's increasing?
Positive.
Yeah, slope should be positive when it's increasing, and the slope should be negative when it's decreasing. So in this case, both problems 3 and 5, I see that it should be increasing when x equals 2, based on my calculations. All right. And for problem 6 is actually the only one that had a negative slope, so that'd be the only one that was decreasing at x equals 2, at the point x equals 2. All right. So sketch a quick graph. All you have to do is put it into your calculator, the function and its derivative. Plug them both into your calculator and sketch a quick graph of it real quickly. And then the second part B, write down the range of values for x for which the function is increasing. So when's the slope positive? All right.
Do we graph the
So feel free to use interval notation or set notation when you're doing these intervals that's increasing or decreasing. So prime note, I'm sorry, say that again.
So how did you find that for number 5?
For number 5, so looking at the graph, right? Whenever the green is above the x-axis, that's increasing. So right there, when it hits negative 1.414, comma 0, that's when it switches from increasing to decreasing. And we can see that here on the blue line too.
It's your iPad, not your screen.
Oh, sorry. Yeah, sorry. We'll switch that over again real quick. So looking at the graph, positive, and then it hits 0 right there, and now it's in the negative y values. That's when it's decreasing. And then even here, the green line is still negative y value, so it's still decreasing. And we can see here the blue line is decreasing, 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 and then it turns a corner here and starts increasing. Well, it happens to turn the corner right when the green line is crossing the x-axis at 1.414. And we can see that here as well. That's where it's turning the corner. So that's how we can identify it. That's what the point of the green lines is. The derivative is. The derivative just helps us because, hey, when we're in positive y-axis on the derivative, that means it's increasing. When we're in negative y-axis, that means it's decreasing. All right, does that help explain a little more?